All right, so what I want to do is I want to now get to the real lectures of the course. So we're going to start things now. How many of you have taken real analysis? Okay. If at all possible, it would be great if you could take real analysis as well as measure theory by Monday. That would allow us to have a really good theoretical. We can even make it next Wednesday. We can push it back a little bit. That would allow us to do things very rigorously. As this is not going to happen, what we will do instead is give you some sense of why you need to be careful. Okay? So this is one of the troubles. Math is not supposed to be something assumed on faith. Things are true because I can prove it to you. Things have to follow from the axioms, from the definitions, and the laws of logic. So what I want to do today is I want to give you a sense of why you need to be careful. The real one that I would love to do is the Banach-Tarski paradox, but that would be far, far too much afield. So what I will do instead is I will do Russell's paradox. How many of you have heard of Russell's paradox? All right, this is a good one. And so this is from the early 1900s. Frege was finishing his monumental work on set theory. And I believe Russell was a graduate student and said, well, what about the following? And this is one of the classic oh shit moments in mathematics, where Frege realizes his entire theory comes crumbling down. That people were too cavalier in terms of what makes a set. And people say, well, a set is just a collection of objects that have a common property. So if I have a property P, all objects possessing property P form a set, and I can do various things with them. So we will call the set R in honor of Russell. It's going to be the set of all x in the universe such that x is not an element of x. Most things are not elements of themselves. Okay? If you look at the set of real numbers, the set of real numbers is not itself a real number. You have to think long and hard to try to find an element that actually is an object that is an element of itself. Okay? Yes?
Is there?
Yes?
Even prime?
Well, but is the set of even primes an even prime? It's not. It's the set containing the even primes. If you look at the set of teams that have won a World Series, give me examples. Be very careful which one you say first. Yes? Good example. Other ones. Braves. Yankees, Cardinals. You really need to put Yankees and Cardinals on the list. I believe the Seattle Mariners have yet to win the World Series. Yes? Okay. I know there's somebody from Seattle in the class, and so they would. So it's not the same as the set of all major league teams. There are some teams that have not won the World Series. But the set of teams that have won the World Series is not an element of itself. The elements are the teams. So it's difficult to find something that is an element of itself. We can ask a question about R. So one of the things you want to learn in this class, in your math classes, is what are natural questions to ask. Well, I've just formed this set R. What might I ask about R relative to this set? Yes?
Is it an element of itself?
Yeah. Is R in R? This is a fun lecture to give with a Boston accent. Right? There are two cases. Case one, R is in R. Well, since R is the collection of all things that are not elements of itself, we immediately conclude R is not an element of R, which is a contradiction. So what must be true? Well, you'd like to say then case 2 must be true, that R is not an element of R. But if R is not an element of R, by definition, R is the collection of all objects that are not elements of themselves. Therefore, R is in R, and you also get a contradiction. So the only thing we can conclude is this is not a set. And what this means is we have to be very, very careful. So in real analysis, you will build up numbers very carefully. This is something you should do once in your life and then never, ever, ever do it again unless you teach real analysis. I will just give you a brief introduction so that you appreciate the fact that we are not doing more than a brief introduction. Can anybody give me a set that you know must exist? Yes. The empty set. This is really all we can start with, is the empty set. So we can start with the set that has no elements. From this, we can form a set. What set can we form from this? Yes?
The set containing the empty.
So next, we can get to the set containing the empty set. We now have two sets. We can form another set. It's the set containing the empty set and the set containing the empty set. We could form another set. It's the set containing the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. And you can go on and on and on. If you had to choose a number to associate with the empty set, what number would you associate? 0. What number would you associate to the set containing the empty set? 1. It has one element. What would you associate to this set? 2. What would you associate to this set? 3. Everybody agree 2 is less than 3, 1 is less than 2 is less than 3, 0 is less than 1 is less than 2 is less than 3. We have a set inclusion analog of this. 1 is a subset of 3. 2 is a subset of 3. 0 is a subset of 3. So the set inclusion actually plays the role of less than. We do not want to deal with the integers like this. But it's good to get a sense of how you might try to do the subject. Okay? And you can build up a whole theory along these lines. And so it's basically the science level. You start with nothing, and you see how far you can push this. All right. We will later on today get to the rules we would love to have true in probability. And we will sadly see that a lot of these rules are not always going to hold. Things like Russell's paradox will get in the way. So the real one is the Banach-Tarski paradox, which I talked about early in the semester, where you can divide things up if you allow strange uncountable sets. So we need, unfortunately, to have a little bit of a notion of countable and uncountable. You're not expected to have seen this. I'm just curious, is there anybody here who has not seen the phrase countable, uncountable? Okay, so I will talk about countable and uncountable. If you want more details, please just let me know. Anybody know the longest song in the English language? So we let Aleph naught equal the size of the integers. So how big is this? So it turns out this is the smallest infinity. So it's the smallest infinity. And we say it's basically the countable sets. So the longest song in the English language is alpha naught bottles of beer on the wall, alpha naught bottles of beer. Take one down, right? You'd still have infinitely many. So we need a little bit of a notion of sizes of infinities. If I look at all the integers, and I look at all the integers minus 1, are these two sets the same size? Because they're infinitely many, yes. If I had two finite sets, if they have all elements, but one set has one element more, they're clearly not the same size. One element has one more. But this is trying to formalize that infinity plus 1 is still infinity. So we say A and B are the same size if there exists a one-to-one onto function f from A to B. So basically, if I can find some function which you give me an element in A, it gives me a unique element in B, no two elements of A go to the same element of B, and every element of B is hit, then we say A and B have the same size. So if I look at the set of numbers 0, 1, 2, 3, and I look at the numbers 1, 2, 3, they all have the same size. Basically, just take every number here and shift it down by 1. You might have heard this as the Hilbert Hotel. You have a hotel with infinitely many rooms, all the rooms are filled, and then somebody shows up and they want a room. And they're willing to pay $1 million, so you definitely do not want to turn them away, but you've already promised rooms to everybody else. So you take whoever was in room 0 and you move them to room 1. Whoever was in room 1, you move them to room 2. Whoever was in room 2, move to room 3, and you're fine. What if you had 2 people show up? Shift by 2. What if you had infinitely many people show up? What could you do? We can't shift infinitely often because I have to know where somebody goes. So before I forget, I don't know if I've explicitly mentioned this. When you make a good comment in class, please email me so it helps me get to know you. When I need to write letters of recommendation, I can make something like this. If you make a wrong comment in class, no worries at all. Part of this is I want you to just get used to speaking up. When I was a student, I was always afraid to speak up. It takes time. What could you do if infinitely many people arrive?
Make them shift to all the even ones?
Yeah, shift all to the even ones. So we could do 0, 1, 2, 3, ... shifting to 0, 2, 4, 6, 8. So everyone just goes to twice what they were. And that will free up infinitely many rooms, so if infinitely many people arrive, I can put them in. This seems strange. We're saying that there's as many even numbers as numbers. It all comes down to how you count. And what is your notion of size? And so another way we could look at things is I could look at, E would be the set of all n such that n is even. And I could look at how many even numbers do I have at most n. So I could look at E sub n would be the set of all n. N is even, and n is at most big N. And then I could look at what fraction of numbers are even. So E of n over n, what is that going to be approximately if n is large? 1/2. So about 50% of all numbers are evens. Okay? So if I look at it in this sense, going up to a certain height, looking at what fraction and taking the limit, I will see that there are not as many even numbers as numbers. But if I just look from a set theoretic point of view, they both have infinitely many elements. You can look at other sets. I could look at the set of squares. So S will be the set of all n equals m squared. I can let Sn be the set of all n is m squared, and n is less than or equal to n. And now I could ask, what fraction of my numbers up to n are perfect squares? So approximately how many numbers up to n are perfect squares? About the square root of n. So this is about 1 over square root of n. So this goes to 0 very rapidly. Very few numbers are perfect squares. If you count up to 100, you've got 1, 4, 9, 16, 25, getting all the way up to 100. So you only have 10 numbers, or 11 if you include 0. As you go further, you get fewer and fewer numbers. So we often talk about fractions like this. Okay? The last thing, just to remark about how careful we need to be, is so here's the interval 0, 1. Here's 1/2. And I'm going to draw a line at 45. A question?
Just a question with notation.
Yes.
Shouldn't it be like the size of En over n? So
Sure. Yeah, I should probably put a cardinality sign. Yes. Thank you. So let's look at the interval 0, 1. And here I'm going to put a diagonal line at 45 degrees. So what's the length of this line? Root 2. And so every number here, I can just map straight down or straight up to this line. And this shows you that I can put a one-to-one correspondence of the points in the interval 0, 1 with the points essentially on the interval 0, root 2. I could then take this and then I could map that down onto the interval going up to square root of 2. So you've got to be a little bit careful with infinities. For the most part for this class, we are only going to be looking at countable infinities, sets that are in one-to-one correspondence with the integers, or basically nice solid intervals. We are not going to look at generic sets. This is where you get into measure theory. They talk about special sets where you can assign measures and probabilities to. We will not work on that. So for us, a set is countable if there exists a one-to-one onto function from the positive integers to it. And then we can label our set A1, A2, A3, dot, dot, dot. So there's, I think, a lot of debate as to whether or not 0 is considered a natural number. It's very annoying. It doesn't really matter, right? If I have a one-to-one correspondence with the positive integers, I also have a one-to-one correspondence with the positive integers and 0. In fact, I could even have a one-to-one correspondence with all the integers. So as an exercise, show that all the integers you can put into one-to-one correspondence with just the positive numbers. So we will only be looking at infinite sequences like this. As a rule of thumb, whenever you see an infinity in mathematics, you have to be careful. This is a warning that something dangerous might be happening. So what I want to do is I want to review a little bit of stuff from multivariable calculus. I'm hoping you remember at least taking the class. How many of you remember Fubini's theorem? Not that many hands are going up. What if I say switching orders of integration? All right, maybe next Friday I will play a clip of my son when he was 2 learning how to switch orders of integration. He has a magic bubble wand that he would just wave and it would justify switching orders of integration. In a math department, that is not acceptable. When you're 2, it's kind of cute. For us, you have to justify. When can you switch orders? You cannot always switch the orders of integration. So, Fubini's theorem. So, there's a lot of ways things can go wrong. They can go wrong because we could be looking at an infinite interval or an infinite region, or they could go wrong because the value of our function is infinity. So what we want to do is we want the integral from x equals a to b, integral y equals c to d, f of xy dy dx equals the integral y goes from c to d, integral x goes from a to b, f of x, y, dx dy. We want this to be true. I'm assuming right now that I'm integrating over a nice rectangular region. You can, of course, do this for more general regions. There is no need to write x equals and y equals. Because of the order of dy dx, it's clear which is being integrated first. That said, I think it's worthwhile to have your formulas a little bit more explicit, so when you glance down, you can easily tell which integral is over which variable. We want to be able to switch the orders. So this is true if the integral from a to b, the integral from c to d, of the absolute value of f of xy dy dx is less than infinity. If that is true, then we are allowed to switch orders. How many of you remember this now? Not many hands are going up. How many of you did multivariable calculus at Williams? Okay, keep your hands up. And if you did multivariable calculus at Williams, did they do this theorem? Okay. We don't have that many techniques in multivariable calculus. We have the change of variables, and there's the big three. Right? What are the big three changes of variables in Calc 3? Yes.
Polar, rectangular.
Polar.
I guess cylindrical.
Cylindrical.
Spherical.
And spherical. It's pretty obvious when you use each one. When do you think you use spherical coordinates? When you have a sphere, right? When do you use cylindrical coordinates? When you have a cylinder. Polar coordinates is a little bit harder. It's basically just when you have a nice circular symmetry. That's one of the big techniques. The other big technique we have is switching the orders of integration. Frequently, if you do things in another order, it sometimes makes things easier. And so you want to know when can you switch the orders. So what I will do is I'm going to give you an example where you can't switch the orders of integration to show you that you have to be careful. Rather than doing an example with a double integral, I'm going to do an example with a double sum. You can smear this out and convert it from being discrete to continuous. It's a little bit easier to represent as a sum. So I need to draw infinitely many dots in the upper right quadrant. In the interest of time, I will draw a finite set and hope the pattern is clear. And so I'm going to choose values for my sequence. All right, that should be enough. And then it goes off to infinity in both directions. So this is the point 0, 0. This is the point 1, 0. This is the point 2, 0. This is the point 0, 1. This is the point 1, 1, and so on. And I'm going to define my sequence of terms a, m, n as follows. It's going to be plus 1 here, minus 1 here, and then 0 for all eternity. Over here, it's going to be 0, plus 1, minus 1, and then 0 for all eternity. For the next one, it's going to be 0, 0, plus 1, minus 1, and 0 for all eternity. All right, I'll do one more. 0, 0, 0, plus 1, minus 1, and then 0 for all eternity. Okay? And what I want to do is I want to calculate the sum n goes from 0 to infinity, the sum n goes from 0 to infinity of a m n, versus the sum n goes from 0 to infinity, the sum m goes from 0 to infinity of a m n. So here, what does this mean? It means I first fix an m, and then I sum over all the n. So if I fix an m, I fix a column. What does each column sum to? 0. What's an infinite sum of zeros? 0. I can't give you an easier sum. Now let's look at the other one. Now what we do is we fix a row, and then we sum. What does the first row sum to? 1. What does every other row sum to? 0. 0 is not 1. If you wanted to make this an integral, what you could do is you could define your function to be maybe like a triangle spike or a pyramid spike coming up, and you could make it continuous, and it would be coming up here and would be going down there. It would just be messy, but then you could get a function version of this on reals. This shows us that we have to be careful. We cannot just interchange orders. Right? It has to be justified. And the condition, the Fubini theorem, is that if the double integral of the absolute value is finite, then you can switch orders. It all comes down to whenever there is an infinity, there is a danger. Okay? Any questions on this so far? Okay. For the most part, this is not a class in painful integration. Right? So I am not going to be trying to find painful integrals to do. Most of the integrals we're going to do are going to be Calc 1, Calc 2 integrals. So this means you have to remember your Calc 1 and your Calc 2. But we're not going to use as much of the Calc 3. What is your good go-to techniques for Calc 2? Which ones do you like for integrating? Use substitution. Excellent choice. What else do you like? Okay, what's the splitting apart?
It's u prime d minus
Integration by parts.
that one.
Yep, u substitution integration by parts. What is your least favorite method? Yes. Partial fractions. If you weren't thinking of partial fractions, it's because you blocked out the memory. If you remembered it, you would definitely hate it. It's actually very powerful, and there may be 1 or 2 times this semester where we actually need to use partial fractions to do something. But for the most part, I really do not want to be trying to give you difficult integrals to do. We are actually fortunate that a lot of the integrals we need to do, we can do as one-dimensional integrals, or we'll have two-dimensional integrals over nice rectangular regions, and you can do one dimension followed by the other. Now, what this tells you is here is an opportunity to make the class more challenging or to have it apply in greater generality, is just change what you integrate over. The theory is the same. The algebra, the calculus would then be different. I want to focus on the probability and not on the challenging problems. When I was a graduate student at Princeton, I was teaching multivariable calculus one year. And we had problems such as you have 2 cylinders intersecting at right angles, calculate the volume of the intersection. And I asked at the end of the semester, how many of you liked problems like this? Okay, we have some control. We can change the curriculum for next year. Should we remove them? And what did the students say? Good. Why did they say no?
Is there one if they know how to do it? Or they like the challenge?
Nope. Yes.
You probably add harder stuff.
Nope.
They want everyone else to suffer.
They wanted everyone else to suffer because they had suffered. And I just remember smiling and said, you know, I had this conversation last year. And nobody was willing to make the break. If you look at what's being taught, a lot of what's being taught in Calc 1 and Calc 2 is not what was being taught when I was a student. There are these things called computers, which are now accessible, and they can do a lot of the calculations for you. So it's really, what do we want to emphasize? I want to emphasize the probability thinking. Right? But I do want you to be at least aware of the issues. All right. So section 2.3, outcome spaces and events. So now we're beginning to get to the good stuff. All right? We want to find probabilities of events. So we're going to have omega is going to be our outcome space. And then events A will be subsets of omega. And what we want to do is we want to assign probabilities to these events. The difficulty is we can't assign probabilities to every event. And so I've mentioned a little bit the Banach-Tarski paradox. I will do another one today. Right now, I will allow you to develop probability theory. You may choose what you would like to hold. And if it's reasonable, I'll accept it. And then we will see if the world actually supports your view. All right? What should be true about the probability of some event A? If you, yes.
Less than 1 and less
Yeah.
or equal to 1.
Okay. In 0, 1. All probabilities should be between 0 and 1. Yes.
If you have a probability A and then a probability not A, they should be equal.
Good. And then probability of A plus probability, we write that as A complement, should equal 1. Either A happens or it doesn't. These seem like very reasonable rules. How many times have you heard somebody say, we gave it 110% today? Can you have a value that's 110% of the safety value? Absolutely. Can you give more than 100%? Yes.
Couldn't you oversaturate something in chemistry?
So there are some interesting situations like this, and it is worth talking about this. So you can have a supersaturated solution where you started off at, is it a higher temperature? and then you cool it down, and you will then have it more saturated at that temperature than you would expect. But in terms of probabilities, can anything have a probability greater than 1? I am so sure. No. Okay? And you can't have a probability less than 0. So this seems reasonable. This other idea here, that the probability of A plus the probability of not A equals 1, let's maybe generalize this a little bit further. Let's say we have a union of AI of disjoint sets. So this means AI intersect AJ equals the empty set if I is not equal to J. So if I and J are different, then there is no element in common with AI and AJ. What should the probability of the union of the AI equal? If you had your wish list, yes. It would only be 1 if the AIs form the entire space. I'm sorry? So I've got the probability of the union of the AI should be what?
The sums.
Yeah, the sums of the probability of the AIs. The probability of the disjoint union should be the sum of the disjoint probabilities. This is similar to something you will from calculus. The derivative of a sum is the sum of the derivative. This is a really nice rule. We've actually already seen an example of this in this class. Not today, but in this semester. Anybody remember when we used this? First day. What were we doing?
I don't remember exactly.
It might have been the second. It might have been the second day. It's not that many days. This is the third day. The basketball problem when we did Bird versus Magic, right? What's the probability Bird wins? We break it up into the probability Bird wins on his first shot, plus the probability Bird wins on his second shot, plus the probability Bird wins on his third shot, and the probability that Bird wins is the sum of those probabilities. And it is not possible for Bird to win on both his first and fifth shot. He's not going to humiliate Magic, and once he beats him, he's not going to continue shooting.
The notation, you have the union of AI, and then you just kind of throw in an AJ. Is that just arbitrary, or?
Oh, what I'm saying is I'm trying to just take 2 elements.
Okay.
So if you want, I could call it maybe, instead I could do AI1 intersect AI2 is empty if I1 is not equal to I2. If you want, I can write it that way.
And 1 and 2 are elements of part of AI.
These are 2 different subscripts. So these are 2 different elements of my sequence of sets.
And those are part of AI, like big A on the left?
No, so it's notation. So maybe I have A1, A2, A3, A4, A5. And maybe AI was maybe A8, and maybe AJ was A2.
Okay.
And I'm choosing 2 elements from my list. So I have a sequence of events. So there's a lot of notation. One of the things that is troublesome is I am sadly more than double your age. So I have been teaching this and doing this longer than you've been alive. So just for me, I am very used to the notation at this point. So I will try to always say what the notation is, but if ever something is unclear, please just speak up and ask. So we're just choosing 2 different elements. This seems very reasonable. But we have to be very careful. I've actually been extremely sloppy, and I was deliberately sloppy, as opposed to the times later in the semester when it's accidental. What should I have really written when I have all this stuff?
You should have had some index set.
I should have had some index. So I could kind of cheat and just put an I underneath, but what's the range of I? And so the danger in mathematics is always when you have to deal with an infinity. We can't deal with an uncountable collection of things. We can only deal with a countable collection. So again, when in doubt in this class, if you need a result, it's coming from your analysis. So we've talked a little bit about countable sets. So x1, x2, x3, da, da, da. A set is countable if I can enumerate it. And I can put it into one-to-one correspondence with the positive integers. Otherwise, it's uncountable. So the first question is, do uncountable sets exist? There are uncountable sets. So the real numbers or the numbers in 0, 1, these are uncountable. And so it is almost a requirement at this point to do Cantor's diagonalization argument, so I will do Cantor's diagonalization argument. How many of you have seen Cantor's diagonalization argument? Okay, try to look interested, okay? So what I'm going to do is I'm going to show roughly that the real numbers are uncountable, and I'm only going to look at the numbers in 0, 1. I'm going to do this fast because this is not a class in real analysis. I just want you to be aware that there are sets that are of larger size than the integers. I'm going to write all the numbers in 0, 1 in their binary expansion. I'm going to use zeros and ones for the digits. All right, so I've got my first number, x1, which is point x11, x12, x13, x14. I've got my number x2 is point x21, x22, x23, x24, and so on and so on. And then here's xn, which is dot xn1, xn2, xn3, da, 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 da. So imagine the real numbers were countable. So if they're countable, then we can order them. And then what we're going to go through is we're going to go through and we're going to form a new number where if we had 1 here, we put 0. If we have 0 here, we put 1. If we have 1 here, we put 0. If we have 0, we put 1. And this will be a new number that disagrees in the nth spot with the nth number, so it can't be on the list. The only thing you have to be careful about is, well, what if I have some numbers have two different ways of writing them? 1/2 is either 0.1 or it's 0.0111111111. This is like the 9 repeatings. You just have to be a little bit careful about that. Okay, so we don't really need to go into too much detail. I just wanted you to be aware of something like this. There are uncountable sets. And the reason this is going to cause problems for us is we can't deal with uncountable unions. So a countable union, you give me any element in the set and I know when I will get to it. I have some assignment that takes my positive integers to your set, so you give me an element and I will know when I get to it. With an uncountable set, I don't know when I will get there. So there's a lot of interesting axioms in set theory. There's an axiom called the axiom of choice, which I believe gives too much power to mathematicians. Some of the algebraists here have no trouble at all assuming it. I think it gives us too much power. Here is where we have some issues. So let's consider the interval 0, 1, and this is equal to the union of x ranging over 0, 1 of the set containing just the singleton x. I want to put on a uniform probability distribution. Right? I realize we have not defined what that is, but you should have an instinctive sense of what uniform is. I want everything to be equally likely. So what should the probability of each singleton be? It should be independent of the x I choose, right? This should be equal to c for all x and some, well actually I'll do p for probability, and some fixed p. I want everything to be equally likely. Well, if our assumption over here, our wish list, was that the probability of a disjoint union is the sum of the probabilities. If that were actually true, well then what would that imply over here? Then we would have the probability of the union x in 0, 1 of all the x's is equal to the sum of all x in 0, 1 of the probability of each x, which would be is sum x in 0, 1 of p. And now we're dead. There's no value of p to put in. If p is positive, this is plus infinity. If p is 0, I've got 0 times infinity. I'm not quite sure what 0 times infinity is. This is not looking good. We can't break sets into uncountable subsets and work with the laws of probability. We have to break things into countable sets. This is why with the Bird magic, Bird wins on his first shot, second shot, third shot, fourth shot. It's a countable partition. And going back to what you were saying before, that if we just partition something into mutually exclusive options, then the sum of those probabilities should be 1, because it's got to happen somewhere. That's what we want going on. But over here, this is telling us that the assumption that the probability of a disjoint union is the sum of the probabilities, that's too strong. We can't have that as one of our assumptions in probability. We need to be more careful with how we deal with infinities. Yes?
Wouldn't the same problem come up for like a countably infinite set? Like if you tried to do a uniform distribution for all the integers.
So if we wanted to do it like that, we can't put a uniform distribution on all the integers because there's infinite many. Absolutely correct. But we could put a uniform distribution on 0, 1, but then we've got to be very careful as to what do we mean. And we only allow ourselves to look at nice intervals. Nothing with holes, nothing with uncountable pieces. But if there are infinitely many pieces, you cannot have everything equally likely. As a warning about 0 times infinity, how many of you know what the product of the slopes are of two perpendicular lines? It's -1. Now, here's an interesting thing. Let's say the lines are parallel to the coordinate axes. What's the slope of this line? 0. What's the slope of this line? Plus infinity. So in this case, infinity times 0 is -1. Because if you look at it, if the two perpendicular lines are not quite parallel with the axes, it's -1, -1, -1, -1, -1, undefined, -1, -1, -1, -1. It makes sense to define it as -1 in this case. So whenever you have a 0 times infinity, it can take on many different values depending on how the process goes. You have to be careful. This is why I want to spend so much time in the beginning of the class just warning you about these dangers. Going back to this, we have to erase this. This is gone. This is not going to be one of our laws of probability. If you could write the laws of calculus, which rule or rules would you change? Yes? Product rule. So, dream rules. The derivative of f times g is f prime g prime. And the derivative of f over g is f prime over g prime. Right? Wouldn't that make calculus a lot easier? Not true. Right? We can't use either one of these. All right. I will end with one last warning from calculus. And then it'll be a good place, I think, to stop today. So there are some rules which you've proven, but you may not have realized how restricted your proof is. So does everybody remember the sum rule? The derivative of a sum is the sum of the derivatives. Derivative of a difference is the difference of the derivatives. You only did that for finite sums. Technically, you only probably did the proof for the sum of two functions. You prove if you have two functions a and b, the derivative of their sum is the sum of their derivatives. If I give you three functions, a plus b plus c, we are technically proceeding by induction. How many people have not seen proofs by induction? Okay, we should talk at some point. Hopefully this should have been done in a linear algebra class. But the way you do proofs by induction is you prove the base case first, and then you show that you can assume the inductive step. You assume it holds for k terms, and then you show that it implies it holds for k plus 1. I know that if I have a sum of two functions, the derivative of the sum is the sum of the derivatives. So I can write this as a plus b plus c, and then take the derivative. Now I have a sum of two functions. One function is the function a plus b, and the other function is the function c. This is so much fun to write on the board. So I get to write a plus b prime plus c prime. Technically now, what's my next step? With parentheses around it. A prime plus b prime plus c prime. And now what do I finally get to do? Now I can drop in and say, well, look, addition, it's a commutative, it's associative, whichever is the right one to say. Order doesn't matter. And then this proves that if the derivative of a sum of two functions is the sum of the two derivatives, then you also have it for 3, you also have it for 4, you have it for any finite number, but you do not have it for infinitely many. And so these are just things you need to be careful about. Is at some point we might have infinite series expansions for some of the probability functions we're looking at. And we might want to differentiate term by term. We do not always have the ability to differentiate term by term. Yes?
So is there no like sort of analog of the inductive step for like infinite sets where you can prove something for like finite sets and like say, oh, and if you multiply it by infinity it works, or something like that?
Let's see, how much time do we have? There are things you can do, and you can show that if I have certain convergence properties, everything makes sense. Right, we should have just enough time to end with the following. My physics professor showed this to me. Some of my students who have had classes with me will already know this one. I'm going to define the symbol integral acting on f to mean the integral from 0 to x of f of t dt. And I want to solve integral of f equals f of x minus 1. You should be thinking f of x is e to the x. Because when I integrate e to the t, I'll get e to the x minus e to the 0. So the solution is f of x equals e to the x. I will show you now how to solve this. Let's see if I can do this right. So I get 1 equals f of x minus, I'll try this, f minus the integral of f. So I move 1 over, and I move the integral over. This is the same as 1 equals 1 minus the integral acting on f. So this is the same as f is 1 minus integral inverse acting on 1. I apply the inverse operator. I use the geometric series expansion as 1 plus integral plus integral integral plus integral 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 acting on 1. Right? Integral of 1 means the integral from 0 to x of 1 dt, which is just it's just going to be x. Then integral of 1 will be the integral of the function x, which now becomes t, from 0 to x dt. This is now going to become x squared over 2 factorial. The next one, integral on 1, would be the integral of t squared over 2 factorial from 0 to x dt becomes x cubed over 3 factorial. So when you do this out, you will actually get the series expansion for the exponential function. You can actually justify this. It's not just a formal calculation. But then you have to decide, what does it mean to have an operator? What does it mean to have an inverse of an operator? When can I use the geometric series formula for the inverse of an operator? You know, when I have something like 1 minus something inverse. So it's similar to the induction. It's you want to know, when can you justify this? It comes down to a lot of epsilons and deltas and showing that you can have things converging and break things up. All right, so this is a good place to stop. We are still trying to find rooms for the review sessions. I hope to have later today knowledge of when they will be tomorrow.